Okay. Well, I think people are still filing in, but to be respectful of everyone's time, I'm very excited to kick us off. My name is Charmayne Lonergan. I'm an assistant professor at the Missouri University of Science and Technology, and currently the chair of the Energy Materials and System Division. We have decided to put on this webinar to highlight nuclear related topics in Missouri and beyond and the perspective. And this is joint with the Greater Missouri section, which is chaired by my husband, Dr. Jason Lonergan, who's a research professor at S&T as well. So it is my pleasure to introduce Dr. or Professor Joe Newkirk. He is the founding chair and professor of nuclear engineering and radiation science at S&T as well. He's also an associated faculty of manufacturing engineering, has a courtesy appointment in the MSc department, and is also a research investigator in both the Materials Research Center and the Center for Aerospace Manufacturing Technologies here on campus. He is a fellow of the ASM International and Alpha Sigma Mu. His education includes a BS and MS in physics from Miami University and a PhD in material science from the University of Virginia. And I'm happy to say that he taught me kinetics, or as much as I was willing or able to receive in grad school. So without any further hesitation, Professor Newkirk, please continue or start whenever you're ready.
All right. Thank you, Charmaine. And you were always a good student. I will say that. At least I'll say that in public. No, no, seriously.
Thank you. I paid him to say that for anybody that is interested.
That's funny. Um, so as I migrate my way into getting this share to start, I just want to say thanks uh, for joining me. And I I wish I could see you all. I certainly like much better to talk to people directly, but I will do my best at talking to this camera and imagining all of you out there listening to me. So as you see the title there, we're talking about deploying, and so we know nuclear's been around, right? So in the 50s, people began to talk about the atomic age, just like there was the industrial age and the iron age and the stone age and all these different great transitions in society. The feeling in the 50s was that atomic energy was going to transform our world. And the reality of that, of course, it isn't quite gone that far. But we're going to look again at what makes nuclear so interesting, and today why there's such a great excitement about new nuclear and how do we deploy that, and using the state of Missouri, which we all know and love, as an example of what's going on in this state. Other states, Pennsylvania, Texas, North Carolina, even Kansas, as I'll show, all have their own things going on in terms of nuclear. So on January 13th, many of you hopefully noticed that Governor Kehoe, who was given his State of the State address, announced that Executive Order A2604 was enacted, which reads basically that I, Mike Kehoe, Governor, do hereby establish the Missouri Advanced Nuclear Energy Task Force. So this is a great thing because Missouri had been, as I'll show, kind of stick in the mud about nuclear, and now Governor Kehoe is on board with looking intelligently at how do we deploy nuclear. So the task force, I'll mention a few things about it later, but Missouri S&T will be a part of this. We are invited to be members of it, as our chancellor right now is moving quickly to establish us as the nuclear campus here. Division of Natural Resources is already coming to visit us to talk about how we can work together. And there's a lot of companies that we take calls from today that are saying Missouri is a great place, we think, to maybe put our first reactors for our companies. Now, like I said, it's not just us. Kansas announced in September that Evergy, the energy company there, and TerraPower, one of the new nuclear companies, are looking at the possibility of putting a next gen nuclear power plant there in Kansas. Also, on a separate article coming out a month later, Kansas could be the testing ground for a nuclear reactor built a mile underground. So Kansas was chosen as the first site for this company's underground reactors. So as we go through the talk, um, I apologize if this seems a little tutorial in nature, but I think it's very important that we all are on the same page to understand everything that's going on and why it's so important. So briefly, I'm going to talk about the case for energy and how important that is to society. Then we'll look at why is nuclear so special. Finally, we'll get into the nuclear deployment and then follow up with kind of what's needed as we go forward with this, including what's needed in terms of materials. So energy is critical to society. That's my claim, and I can prove it, and other people have. Our new Department of Energy Secretary, Chris Wright, has a great report out of one of his companies on just how important it is. But just very briefly, new energy sources have transformed society. When mankind started to tame animals, he gained more power through that, and you can see the horse-drawn plow. Later, steam came along, and Henry Ford had a giant steam engine. If you've ever been up to Michigan and Dearborn to see his original steam engine, it's a monster. And all these belts ran all these lathes and drill presses and everything to make cars. Uh, then we went to internal combustion, and you can see the tractor in the background, which once again has higher energy in a good package. And now today we have a lot of rechargeable implements. I have rechargeable things at home. I even had a little snow shovel that I use that's rechargeable. And it's really good for cleaning off the walk and some of the driveway. But we're looking for higher energy density. In other words, batteries with more power in a smaller package. Always we're looking for more energy in a smaller package. And that's where the term energy density comes in. So energy is the basis for our society. We really, none of us who are alive have ever lived in a time where there wasn't a lot of energy in the United States. Now, somebody from certain foreign countries, particularly in certain parts of Africa and South America, maybe have experienced other. But clean water, fertilizers for crop production, medicines, medical equipment, materials of construction, transportation, education, residential heating and cooling. These things and many more are all based on available energy at a certain cost here in North America. The table basically just says when you talk to people, high energy costs will cause people closer to the poverty level to forego things such as good quality food, medicine, or educational opportunities for their children. So energy, the energy cost, energy density, these things are all vital to Missouri's economy, its growth, and its citizens. And if you look at the charts on the right, it basically says both life expectancy and percentage of people living in poverty rank with energy consumption. So one way to look at this is on this time basis that says the more fossil energy, the better. But we can look at this in current times by just saying poor places like sub-Saharan Africa versus places like Europe and the United States, the lowest energy producing places are also the poorest. So you can look at plenty of statistics on this. And I'm not going to take the time to go through them all. That's a whole nother treatise. But energy costs affect the poorest of the population the most. And currently in Missouri, there's pressure on citizens from high energy costs. Just listening to the St. Louis news this morning was talking about high energy bills are hurting senior citizens. Agriculture, once again, agriculture is very energy intensive, whether it's livestock or whether it's cash crops. There's a lot that goes into it. You can see from this chart that in terms of the percentage of the budget of a farm spent in order to bring in their crop in at harvest time, that fertilizer, pesticides are huge. Fuel for things such as the tractor, electricity somewhat for lighting. All of these things are a huge cost to the farmer. And when these things are expensive, they either starve or they pass those costs on, in which case we pay higher cost for food. It's interesting. If you look at Missouri, 2024 statistics, the latest I could find, currently our electricity is still 50% produced by coal plants. It's kind of interesting that the charging station off of I-44 right here in Rolla, right off one of the exits, people come in to charge up their cars, and I wonder if they know that 50% of the electricity they're putting into their cars was generated by coal. It just makes me wonder sometimes. It's interesting when I was preparing that I had 2023 statistics and the all carbon free category went down a percent. It was 28% in 2023. It's 27% in 2024, which means basically we're losing ground on carbon free energy. If you're wondering why, a lot of that has to do with the use of natural gas. But we are still using fossil fuels in a very high rate here in Missouri. Now, 5 years ago, if you looked at the projection for future energy needs in the United States, it was predicted to be basically flat. They were saying, hey, higher efficiencies offset by a little more generation, and it's all going to be pretty much the same. Well, that has changed in the last 5 years. The energy situation is dramatically different because of a couple of things. One is data centers and now hyperscale data centers, which are even more energy intensive. The electric vehicles that have been pushed and are more prominent now. And if we continue to go that way, we'll require more electricity to fuel. And of course, industry. Industry needs more energy, and the reshoring of manufacturing is bringing manufacturing back to the United States, but that adds even further to the energy needs of the United States. Now, statistics says that in general, manufacturing is only uses 21% of the energy used in manufacturing is electricity. The rest is heat, and that could be burning natural gas and other fossil fuels once again to generate that. Uh, and we'll come around to new nuclear and how it can potentially offset some of that as well. Looking just briefly at data center power, the whole world consumed estimated, uh, somewhere around 300 terawatt hours in 2021. It's expected to double because of data centers by 2030. And that doubling will lead to it being 21% of the whole world's energy will be consumed by data centers. That was before hyperscale, so I couldn't find anything more significant. If you look at the chart, it basically says by 2030, it's expected that in the United States, it will be 10% of all electricity will be data centers. Once again, AI is changing that. But one of the things about AI or conventional data centers is they can't have a disruption in power. So they need 24/7 reliable power, which is one of the bugaboos about a lot of the renewables is they aren't necessarily reliable. They can add to the mix, but they can't support huge base loads that need 24/7 power. And mentioned carbon. We mentioned that in industrial heat, residential heat. A lot of that is still based on fossil fuel. There are propane tanks here around Rolla that people use for their heating. My house is heated with natural gas. Transportation, obviously, gasoline and diesel, two of the big ones. Even if we go to hydrogen, hydrogen will have to be produced, and right now it's produced from natural gas. So, any way you look at it, there needs to be another answer if we're going to stop the carbon generation. And solar and wind cannot add heat except through less efficient electric heat. So, what about nuclear? Nuclear over the decades has shown itself to be clean, reliable, and secure. Um, Case after case, earthquakes in Turkey to tornadoes in Missouri, that nuclear keeps going when others have to shut down. But let's go back to basics and look at it a little bit differently. If we look at any kind of chemical reaction, so we're burning fuel, we're having carbon and oxygen at 7.68 EVs released per carbon and oxygen interaction. All chemical energy is based on this scale, EVs per atom, EVs per couple atoms, EVs per molecule. And you think of some of the largest chemical reactions, whether that be TNT or what it may be, that's just a lot of mass being converted in a very rapid period of time. Any chemical reaction is in the order of 1 to 10 EV. Nuclear, any interaction here is on the order of 1 to 8 million electron volts per nucleus. And the numbers in front, by the way, are just the atomic numbers, so it's not saying 28 irons. If you look at uranium-235, atomic number 92, it's almost 8 million EV per fission atom. If you look at hydrogen potentially for a fusion reactor, it's about 1 EV per hydrogen atom compared to the 8 for carbon and oxygen. So basically, radiation is very powerful, which of course means there's a danger. But at the same time, it's so powerful, it's used as a cancer treatment. And it's used for imaging and other things. So radiation science. The nuclear reactions themselves being a million times greater, it doesn't matter whether it's fission or fusion. And the higher energy density associated with these sorts of numbers means that for a given amount of power, it can be in a smaller package, or you can use less nuclear fuel to achieve the same power. And concomitant to that is that it generates less waste. A lot of people are concerned with nuclear waste, but as a just general argument, nuclear produces less waste here. And if we look at this idea here, I just had some fun. I said, okay, if nuclear reactions are a million times more energy than a chemical reaction, think about a car that gets 25 miles to the gallon, and now on nuclear gasoline, it gets 25 million miles per gallon. Or a cell phone may be charged for a day or two. My wife has her screen on all the time, so hers is about a day. Mine lasts for a couple days. But a nuclear battery says you buy the phone and it only lasts for 2,000 years before it needs a new charge. So nuclear energy is not just a replacement for certain other types of energy sources. It is a whole different paradigm in terms of the magnitude that's possible. I say possible because we don't necessarily use the full power of nuclear right now, and that's something we need to change. So energy density. I asked the Navy, how long will one of your aircraft carriers run before you need fuel? They said it's classified, but it's longer than 25 years. So basically, our aircraft carriers can run 25 years plus without refueling the reactors. The only refueling they do is to add more aviation fuel for their jets, but they don't use any to run the ship. Nuclear power plants such as Callaway, Missouri 1 up there in Callaway County, typically refuels every few years, and it's a partial refueling. They kind of rotate the fuel through in order to maintain constant levels. So high energy density, I said, means lower amount of waste. A calculation was made that all the nuclear waste created by all the commercial reactors in the United States fit into one Walmart. A lot of people don't pay a lot of attention, but coal is trucked into a coal plant and then coal waste is trucked to the landfill. So the amount of released waste, some of it gaseous, some of it in terms of solid, is large. And interestingly enough, the burning of coal releases more radiation into the air than any nuclear power plant. So new nuclear, I mentioned that term. Callaway is basically a Gen 3 reactor. It's a large light water reactor with greater than 1 gigawatts of electric power output, and it operates at temperatures that are high temperatures for water and creates steam. Some of the SMRs that you've seen, such as NuScale's Voyagers, are basically smaller light water reactors. And those are also, of course, limited in temperature. Now, one of the things that makes it Gem 3 Plus is that we've taken a reactor and we've updated its instrumentation, added certain controls, and we've made it safer than it would have been when it was built maybe in the 60s, or it's new and it's built with later standards, but still it's based on a similar technology. The uh, the light water reactors have an inherent instability in them, and you need to have active controls. It's interesting that a lot of the military jets that come out today are also totally unstable, and computers fly them, and humans through a joystick just tell the computer what action the pilot wants. So these are certainly safer reactors. But the Gen 4, all the Gen 4 reactors are based around different technologies, and that has two consequences. One of those consequences is almost all of them, to any degree you want to test them, when power is disrupted, they just stop. They're inherently built in with much greater safety factors than the light water reactors. The other thing that you need to remember about these Gen 4s is all of them operate at much higher temperatures. We're talking about 600 to 1000 degrees C would be the coolant. That's kind of a funny term, right? Coolant temperature in these reactors. And this lends itself to applications in industrial heat. So Gen 4, whether it's gas reactor, a metal cooled, or molten salt cooled, you may have heard the term micro reactors. All of these technologies in the Gen 4 is the new nuclear. Now, I include a slide on fusion. This slide is interesting because it predicts that all of these companies will have working fusion reactors in the next 5 to 10 years. Uh, that's very interesting. However, they still won't be practical very soon. The promise of these fusion reactors is undeniable. The problems are significant. First of all, there's fuel issues. Most of those ones you saw, if I go back to that chart, had B-T, which means they're using tritium. Tritium is considered a dangerous material because it's used in hydrogen bombs, and the United States limits people's ability to acquire and use tritium. One of the ways they're proposing to use tritium is to basically breed it in their fusion reactor. But that has not been solved yet. There's issues associated with that. There's materials issues associated with these reactors. These are going to be much higher neutron fluxes. They're going to be, in many cases, high temperature. There's going to be a variety of activation issues. And many of these companies are in dire need of new materials. Had a request just last week from a fusion developer asking us to make some new alloys for them that they think might have promise. And finally, there's the reliability issue. So, question. Nobody has made a dishwasher, but now Maytag has come up with the first one. You don't have to scrub dishes anymore. Wouldn't you like to have one? And by the way, it's a prototype. What does that mean? Well, that means it could break down at any time, that there may be unintended consequences as it gets older. There may be no replacement parts, etc. When you go to the store and say, I'm going to buy a new dishwasher today, you look for something that's warranted. It's known that it's going to last for years. It's repairable. There's going to be parts available to fix issues. All the worst issues with it have already been worked out. It's going to work good. So the day somebody produces a working fusion prototype is not the day that a city like Columbia, Missouri is going to buy a fusion reactor for that 24/7 power at once. So you're going to have to add 10, 20 years of development time beyond prototype stage before you're going to be able to buy a plant you want to use. So what about deployment? First of all, we've got an energy infrastructure. So what we're talking about is adding nuclear into the existing infrastructure. Conventional nuclear power plants like Callaway and the new plants down in Georgia, Vogtle 3 and Vogtle 4, are all in the gigawatt electric range. They are built on site. Everything is trucked there. Modular does not apply to these things, although Vodal tried to use the modular concept. You're bringing skilled workers out in the middle of nowhere to put these things together. Small modular reactors have now been defined on their power rating, can be anywhere between 10 and 300, and those numbers are a little fuzzy. But one group, the IAEA, says 10 to 300 megawatts electric per unit. These are modular in the sense that the reactor is built in a factory to whole and is then moved to site. Some of these could be fueled in the factory and moved already fueled, but they're still going to need refueling. The picture on the top right is a Voyager 6 by NuScale, showing what it would be like. And there's supposed to be some cost offsets. So bigger has some economic value, smaller and being built in a factory has some economic value. So the modules are factory assembled and shipped to a site. They don't have to be in the middle of nowhere on a riverbank somewhere because they're not going to need cooling water, number one. And number two, their smaller size means that the NRC says they don't have to have as big a safety zone. And so they can be actually built close to cities. Microreactors less than 10 megawatts electric, assembled in the factory and shipped whole. And you see that schematic of one company's design sitting in a truck bed. So you would have that, and you would have a steam turbine, and you ship those two, you bolt those together, and you run them. That's the plan. However, one of the things that's really key now is the cost of transmission. So Callaway sits in the middle of nowhere, and all its electricity has to be shipped. Wind farms in western Kansas ship their electricity to Kansas City and to the east, and there's huge costs, both politically and financially, associated with transmission. So if I have a coal plant I'm shutting down and I put a reactor in there to generate heat, I can use the same transmission lines. There's no extra cost. Uh, the smaller reactors being able to be located close to the utilization of the electricity means the lower cost of transmission, and that's another economic plus for the smaller reactors. However, we've got other challenges, and that's associated with the number of nuclear workers, either engineers or nuclear operators or nuclear tradespeople. Uh, we aren't generating that many because of the static nature of not having built reactors in a while. And according to the Bureau of Labor Statistics, we're retiring about as many engineers as are graduating from nuclear schools. So we've got to ramp up. And then the Advanced Nuclear Pathways to Commercial Liftoff that DOE put out in 23, they projected that they will need 14,000 nuclear engineers to become 52,000 nuclear engineers, as well as all the other trades. So what am I going to do? I'm going to start putting out 4 times more graduates than I ever have. That's what we're asking of every engineering school in the country. Now, good news, TVA, the Tennessee Valley Authority, has signed an agreement with Entra1, who is a operator of nuclear reactors, to install 6 NuScale Voyager 12s. So you can see this is just back here in September that they announced this. I've talked to NuScale. 6 Voyager 12s. A Voyager 12 is 12 small modular reactors, so 6 times 12. 72 reactor vessels is what Tennessee has ordered. Right now, we can't build those in the United States, so they're going to buy them from Korea. But this is a real game changer in terms of potential to order, and for NuScale, it's income, it's validation of their licensed design, and now they're going to be ramping up the manufacturing of this. Let's talk about Missouri. In 2021, we came up with our Missouri State Energy Plan. That adopted plan was keep Callaway running, go to natural gas, but don't build any new nuclear. 4 years later, there was a meeting I attended up in Jeff City in May to discuss a new energy plan that they said will take a couple years to come up with. In 2025, they announced in October, that was May, in October, they announced that they're going to hire a contractor to produce a new plan by July of 26. And about the same time, Ameren announced a plan to add 1.5 gigawatts of new nuclear, but it won't be online till 2045. Then in 2026, the Missouri Task Force was created that you saw. Governor Keogh announced it, and the idea is they will report every December on how our new energy plan and the nuclear portion of it is being met. So you can see a very fast evolution in the state's interest in nuclear and in energy, all reflecting back on that change I was talking about. So DNR has initiated a new effort for their state plan. There was a summit held this summer. A retreat was held the day after, and nothing was concluded from that. But now the governor has announced we're going nuclear, and I need people to guide me. So what's needed? If you don't know the department here in nuclear engineering, we produce about 30 graduates each year. We're one of the larger programs in the country for bachelors. Right now, our enrollment has put us on track for ramping up to probably 55 graduates each year in 2 years, and it's going to go beyond that from what we're projecting. There's only 26 current programs, and S&T may be a small school compared to some others, but in terms of nuclear, one of the largest programs in the U.S. So we are dedicated to producing those professionals and helping some of our technical colleges to produce more technical workers. Right now, UMC, otherwise known as Mizzou, has added material characterization capabilities to their reactor mirror, which is 10 megawatt reactor, who mostly produces radiopharmaceuticals, and they are now committed to spending $1 billion. I think it's closer to two now for a new reactor. This reactor is probably going to be based on light water technology. At Missouri S&T, we have a plan underway to uprate the power of MSTR from 200 kilowatts to 5 megawatts. Now, we're talking thermal power here, not electrical power. This reactor can't produce any electrical power. We are now also on a path to install a new microreactor facility, which I'll briefly talk about, and that will produce electricity. It will also produce usable heat. At the moment, we have just signed a master agreement recently. It was last February to have a blanket research agreement with INL, who is the reactor National Lab for DOE. And we have signed a super agreement. That's what it stands for there, Strategic Understanding for Premier Education and Research. One of only 12 schools that INL will give this status to. They will not be a 13th. They have guaranteed that. We're going to have an official signing ceremony here on campus on April 7th. The director, John Wagner, and a lot of his top people will be here. It'll be a day of presentations and all, and some of you may want to come and attend that. But that working with INL, INL has built and operated over 50 reactors out there in the desert of Idaho, and they are going to be leading a lot of the new technologies for both civilian and military reactors. We have recently formed a research consortium, ARC, the Advanced Reactor Research Consortium. And right now, it will be industry members supporting the research, and it's going to be leaning on the strength of this campus in materials, manufacturing, and nuclear. And so a lot of companies have been invited and are now considering the membership and choosing the pre-competitive research. But a lot of them are specifying they need help in nuclear materials. The current reactor, I mentioned the uprate. It would also add Post-irradiation, PIE stands for post-irradiation examination. In other words, we'll be able to look at materials we have irradiated in it. We'll also be doing things with communication to the outside, such as digital twins and cybersecurity. We're going to have to make the building bigger to accommodate it. We're going to have to improve security and safety. Committee has provided a vision for this. They're writing up their report as we speak. The chancellor has already asked that we start the process and get the money for this. We're going to purchase a NuScale E2 simulator, which basically simulates a Voyager 12. This will be for workforce development and also for our educational mission. Right now, we are limited in the number of students we can handle. In order to increase the number of students, we have to increase our laboratory facilities, and this will help us by allowing reactor experiments to be done on the simulator along with the reactor experiments done in the actual reactor. So we're trying to provide a lot of leadership in this time. We're also planning this Powerplex that I want to talk about. But along the way, we got this nice gift from the state, which was awarded back in July when the budget was announced. We haven't gotten $1 yet. We're hoping that that will happen in the next 2 or 3 weeks. But this is supplied by the Department of Natural Resources to their Division of Energy. And we're finishing up the negotiations with them for that. That will pay for the simulator. It will also pay for the Powerplex initial planning grant. So the Powerplex, we have a protoplex on campus. We're building a bioplex, so we're calling this the Powerplex. I'm now being told, if Charmayne's still on here, we're going to have a geoplex. But anyway, the key to this will be an advanced nuclear reactor called the Missouri Integrated Nuclear Energy Reactor, MINER. And that will be based on a Gen 4 technology that we haven't yet specified. The reason we haven't specified it is we want to come up with all the specifications for what we want it to do, and then we want companies to tell us who can do it for what and compete for it. But it will generate electricity, it will generate heat, and it also can distribute that heat and electricity to the campus. The campus becomes a test bed for it. And we'll see there's other places such as thermal storage, battery storage that could be utilized to create this on a microgrid. The heat will be available for industrial people to come in and say they want to work on biomass conversion, desalination, hydrogen generation, ammonia production, etc. here. And it will allow us to basically integrate a new reactor into an existing infrastructure, and that'll generate knowledge that communities, Columbia, Springfield, Jefferson City, etc., can use to make decisions, informed decisions on their desire to purchase and operate reactors. So the reactor would be the center point. It could send heat to the turbine to generate electricity, but it could also send heat to other places around it. Other sources of energy can be integrated into this. It will all be on a smart grid. So right now, we are in the process of starting the feasibility study with outside consultants. The end of the about a year process will have costs and sources of funds and reactor specifications to go to the next stage. The reactor we would choose, we hope, would be a commercial version. We're not interested in a prototype and all the headaches associated with this. So once again, this will generate knowledge. Now, what do we need in terms of materials? Why are companies all asking for more materials work? Well, there's a lot of things that we need. We need lower activation materials for the fusion reactors, so we're not transmuting elements into things that are highly radioactive. Fusion reactors want to take lithium and convert it to tritium. But right now, the materials for that, what's called blanket, which would be basically close enough to the fusion reactor to be bombarded with neutrons, is still not been developed. We need higher temperature and radiation resistant sensors for controls. We need high temperature erosion resistant materials for some of these fusion techniques, which will have high erosive properties. Also, the thermal storage devices will be pumping things like molten salts, and how will those hold up? We need structural materials that are radiation resistant and high temperature, and honestly, it would be great if they were self-healing. We need magnetic materials, both superconductive and high temperature. Superconductive for magnetic confinement, high temperature for solenoids. And this is a little bit pie in the sky, but right now we use our neutrons to generate heat, the low quality form of energy, and then we convert that through steam to the turbine to get electricity. There can be ways of taking those highly energetic neutrons and directly producing electricity. And there's probably some kind of semiconductor or some sort of functional material that could do that. And it would be great if we were developing that now. In addition to materials themselves, we need better methodologies. The answer to the question, can we get new materials faster? INL is devoting some of their LDRD call this year to this. A lot of other people are as well. We've been actively involved in faster test and qualification methods, but we want faster discovery of new compositions, maybe using additive manufacturing or various techniques to make varieties of chemical variations. We need to be able to fabricate these into things that can be test coupons. We need to test those and use the test results to select high quality materials. Then we need to do this in irradiation. After we do that, the testing needs to be to the point where we can qualify these as nuclear materials with that special stamp that says we can build a reactor out of them. INL is suggesting that the process, which is typically on the order of 20 years to a new material that's nuclear qualified, be reduced to 2 to 4 years. So all we want is what everybody wants: cheaper, qualifiable, fabricable, innovative materials, and we want them all sooner. So just to conclude, the atomic age, as it was called, didn't really happen. It didn't really transform society. It just became another energy source. Of course, the military uses a lot in their submarines and aircraft carriers. But now we're looking at a potential explosion of reactors. We've got not only universities and military bases, but others are ordering these, and the volume of reactors, we have just under 100 operating commercial reactors in the United States today, plus some test reactors. We're looking at volumes in the tens of thousands. Some reactor vendors don't have a reactor to sell, but they already have orders. And some of that heat, process heat, can be used to convert carbon sources to liquid fuels. So we could start looking at replacing diesel and gasoline from petroleum to instead creating it from biomass and other sources. Fusion reactors are expected to come online in a decade or so, maybe 2 or 3, but still they're going to come. And we need new sources of transportation fuels at an economic price. So in conclusion, energy is critical to Missouri. Nuclear is high energy density, it's clean, reliable, and secure. That's been established over 60 years, and now we know how to do it even better. The employment opportunities that are upcoming are outstanding. Deploying nuclear reactors, however, means integrating them into current infrastructure and learning how to do that, and starting to use smart grids to balance energy across the entire community. The location of new reactors being close to the sources of usage opens new possibilities for communities to have these. But materials, as always, in everything. We could build better airplanes if we had better materials. We could build better cars if we had better materials. Well, we could build better reactors if we had better materials. And so there's always going to be this driving need for materials as a limitation that needs to be removed. But Missouri S&T is preparing to be a major resource for the state and to lead efforts into the deployment of new nuclear into our communities. So with that, I'm going to stop and hopefully answer a few questions.
Awesome. Thank you, Joe. That was a really good talk. Um, let's see. if you can just have, if anyone wants to ask a question, just please raise their hand and I'll cue you in. So let's start with that. If anyone has a question, here we go.
So Jason, I can't see the
Okay.
question.
Paul, I think you had your hand raised. All right, Paul. I can't hear you if I don't know if you're trying to speak. If not, can you type it into the chat box?
Yeah, can you hear me now?
Yes, yes, yes.
Okay. So I'm out in Washington State, and Helion is proposing to build their first unit here, and they've already actually started construction for a Microsoft data center out here, and
Mm-hmm.
proposing they're going to generate 50 megawatts. I think that's going to be years off, but they're saying they're going to be generating in 2 years. I mean,
Mm-hmm.
I think the quote new gen old technology that you're talking about is probably really going to be the way to go. I mean, part of it, the big part is public perception, right?
Mm-hmm.
We're really scared of the 3 Mile Island thing, and the Russian stuff. And so I think it's a lot of education, right? Just general education about the difference between where we were and where we are now. And you spoke to some of that, but I think that's the big thing that needs to be done is just general education to the folks in the general population.
Mm-hmm. Paul, that's a very good point, and we're very sensitive to that. I didn't obviously talk much about it. We actually have, as a part of one of our teams, is a technical communication specialist who specializes in risky messages, and so we want to make sure that we're putting positive educational things out that we can explain to people. We'll go into communities and explain to them. On the fusion side, the fusion people are trying to avoid the term nuclear so that it doesn't carry with it the stigma that you mentioned about like 3 Mile Island. And they're hoping that they can slide out there and say, look, we're very, very safe. Um, but yeah, I've talked to Helion. A lot of the people at the labs who work in fusion just don't think their timeline's possible. And by the way, I visited ZAP, which is out there in the Seattle area as well. And they have a very aggressive engineering program. But once again, once you get a working prototype going, the ability to put that into Columbia, Missouri is there's going to have to be a lot more work done before you're going to have a reliable unit that you can fuel and keep fueled. So I think they're coming, like I said, but I just think some of those aggressive timelines are just a little pie in the sky.
Yeah, I agree. I mean, they've got a lot of money. I mean, they've Helion's got what, $1 billion at their
Hmm.
disposal, but they're burning through it pretty quick. And when the president of the company was here in town and we had a public meeting with him and his staff, I said, well, you're on, I think they're on their sixth or seventh generation unit. And my
Hmm.
question was, how many kilowatts have you put back into the grid? And
Hmm.
the answer is none.
Hmm.
Because they're not there yet.
Yeah.
So I mean, I think we'd all like to see it, but I think it's a long ways off, like you said.
Yeah. Once you get a sustained reaction or a pulse reaction, however the technology goes, you still have to take the heat from that to make steam and turn a turbine. Um, And then you have to have that fuel cycle. And I didn't go into a lot of detail on that, but you have to refine your lithium and get higher levels of lithium. Is it 5, the isotope? It's the non-normal isotope of lithium, and then you can convert that to tritium. Um, and they've not done it yet. So, as you know, you can have all the best plans on how you're going to get step by step to a certain point, but you're going to find some setbacks along the way. They'll get there if they have a good engineering approach, which I think they do. I just say those promises are just bringing in money from investors. That's I hate to put it that way.
Yeah. Well, but I mean, their technology supposedly doesn't go to steam to generate. They're counting on more like a generation system, almost like, you know, the neutrons are going to pass through the field like a generator when you pass the magnetic forces to generate electricity in the generator. That's their claim to fame, that they can skip, you know, one portion of it. But, you know, I think that's a ways off. We'll see.
Yeah, they got to prove it. By the way, the neutrons are neutral. And so somehow you have to generate charge. And that's what I said. I would love for people to be working today on how we could do something better than converting heat to steam and use those neutrons directly. That would be using more of that million times greater energy potential. And that's the future. And it means we all have jobs.
Yep. Yep. Well, thank you. I mean, we certainly need more power, you know, and to think that we don't, I mean, you know, even out here in the 3-state area, we're going to need, I think they said 70 gigawatts in the next 10 years of additional power, you know, and you're not going to get that from wind and solar,
Right.
you
Exactly.
know, because it's just not reliable. And they tried that one big solar one down in California, right in the desert with mirrors, where they were basically melting salt, right?
Mm-hmm. Yeah.
And you know, that was quite a boondoggle, right? No one ever wanted power. It's so expensive, and it's shut down already, right?
Yeah. Yeah.
But
Well, thanks, Paul.
yeah.
We need to go on to the
Hey,
next
thanks,
question.
guys. Have a good day, and appreciate all your information. Good
Okay,
luck.
got it.
Yeah, thank you, Paul.
Jason, we have one question in the Q&A, and we have one person with their hand up. What do you want to do?
Let's do the Q&A. That one was up first. So
Okay.
can you see that?
I actually, it popped up. I can now. I
Okay.
couldn't earlier, but it talks about meltdowns, and in particular, you know, what's the plan to address that concern for the public? You know, it's very interesting that when 3 Mile Island occurred, I think something on the order of 50 nuclear reactors were canceled. And then sometime around, what are my dates? That was at the early 90s. They started talking about the nuclear renaissance, and people were starting about building new reactors again. And then Fukushima happened. And now we are past Fukushima. So public opinion on reactors tends to go way down at some event and then rise as time passes. But that's obviously a very passive approach. The more uh, the more practical approach is to get the message out on their concern. First of all, address their concern. Yes, the big reactors have that potential to melt down, but we've been operating them since the 60s, and we have learned a lot. Steam explosions killed a lot of people in the early days, and we eventually went away from steam to internal combustion, and that killed people. So there's always this technology learning curve, but if the adoption of that technology is prevalent, it's going to happen. We're just going to learn to use it. So if you ever watched the documentary put out by Oliver Stone called Nuclear Now, he was a former nuclear uh, protagonist who convinced himself to become an advocate. And he talks about the politics of petroleum companies putting out bad press in order to push public opinion to get rid of the competitor called nuclear energy. So there's a political side. Yes, there's a public perception side. There's the reality and the data that's been generated over decades. And so that has to be put together into into a good message, and people need to be educated. Uh, I'm a little bothered by the data center issues. Data centers come in and promise all these positive things, and then people learn that, well, maybe not all those positive things are going to be as positive as they said it was, and then they feel betrayed. We can't do that to the public anymore. You've got to go in there to be honest and talk to them about how we're going to guarantee safety because we can. So that's kind of a short answer to that. I can go down the list.
I'm gonna let I think it's Samdeep. I
Mhm.
apologize if I butchered that. I'm gonna let him come in.
Sure.
Hi, Professor Newkirk. This is Soumyadeep from
Yeah.
PNLM.
Yes.
What?
Yes. I know. Well, we've talked.
Yeah, one of your student. Uh, those old good Oladies. So regarding it being a ceramic conference division,
Hmm.
so I was wondering if you can uh, put some comments on the materials challenges that,
Hmm.
especially for the Gen 4 and also on the fusion side. Some of my
Right.
friends,
Right.
yeah, some of your thoughts if you share.
Yeah. You notice I just had like two slides kind of capsulating things because it could be a whole seminar in itself. And I had a picture, and I forgot to mention it, of the cascade, displacement cascade that a neutron causes when it enters. In that case, it was a heavy metal, plutonium. Uh, Understanding that damage mechanism is so critical. So a lot of metals will self-heal to a part. And we look at the damage that's caused instantaneously, and then the damage that lingers. And of course, ionically bound or covalently bound materials have similar actions, but it's just a little bit different in the way it occurs. We have materials that swell. We have materials that lose strength. We have materials that can become activated and have become hazards. And I'm not going to push solutions, particularly in an area that's not as my strength. I'm more of a metals guy. Jason and Charmayne can talk a lot about non-metallic materials a lot more than I can. But the understanding of the mechanisms for that, being able to predict it, because right now you can spend a year getting a little sample into a test reactor. You can spend a year irradiating it, and then you can spend a year waiting for it to cool down, and then you can start examining it. What did we learn? It's such a slow process. So what we need is more understanding of covalent ionically bound materials interactions along with the metallic. And we need design strategies for the applications.
Mm.
But for functional materials, it's a little bit different. There we're looking at it's a shape memory type of event, and what does neutrons do to that? We're looking at oxygen sensors. What do neutrons do to change that? Without any specific answers to your question, we could go down a lot of trails and look at where we need more. And the difficulty of doing that even for a non-irradiated situation, and then adding the difficulty of irradiation testing to that. So I'm going to leave it at that, and maybe Jason and Charmaine can follow up with another webinar and go deeper into some of the ceramic material challenges associated with this. But in
Yeah.
general, like an aircraft, we want lighter, cheaper, and stronger, and with higher modulus, and radiation resistant materials. We want self-healing, and we don't want the properties to be changing. We don't want the dimensions to be altered, and we don't want the material to be activated. But we still want it to do all the other things that you do when it's non-irradiated.
No, no, I hear you. I hear you. And that, like, the irradiation becomes that fourth thing that
Hmm.
becomes another challenge to handle. And maybe some sort of like a faster creep kind of thing, like a
Yeah.
creep experiments at a faster rate, like a accelerated testing. So that sort
Uh,
of,
you've hit it on the head here. If we're looking at the time to test something just for tensile testing, with the radiation schedules and iterations and all that, and then
Mhm.
you add something that's also time dependent like creep, um, this is where the 20 years comes in.
Yep. Yeah, makes sense. Yeah. Oh, thank you.
You bet.
Mhm.
So I think there's still one more in the Q&A
There's
on
actually a couple
materials. Okay.
that I'm looking at right now. The next one from Scott Barnhouse is about the hype around building nuclear power plants for data centers. When do you believe that the first one of these will be built, and how big will this market be? As I understand it, in terms of built, we haven't built any new reactors since Vogtle 3 and 4, so it hasn't happened yet. There are data centers being built next to existing reactors, which is a different issue because there's only so much energy to come out of that plant. And when the data center says we'll pay more money to guarantee that we get a big portion of it, then suddenly the community's prices go up, and that's where people are getting really mad at data centers. But the all the hyperscalers are now working with a few people. I think Kairos and TerraPower and Oklo are three that have orders to put reactors somewhere with the idea that eventually there'll be a data center. In addition to that, we're not even talking about military. So the Army, the Air Force, and the Navy have all agreed that they need new generation reactors on their fixed bases. And that forms a core of reliable energy. If the community's energy generating capabilities were cut, that base has to have its core functions still powered. And so they want to put those on there. And of course, guess what? The military is also going to AI and data centers. So they need it as well. When do I think the first of these will be built? I think we're looking at maybe for finish and operation, probably 2032, maybe would be a guess. Some people are saying it's going to be 2030. I think that's possible, but really aggressive, and I'm not sure that's going to happen. How big will this market be? That's a great question. The way I look at this data center and AI stuff is that it is the big driver right now. 5 years from now, are we going to be worried about building more data centers, AI, or is it going to be something else? Um, but right now, it is going to be the early adopter. So I thought the first adopters was going to be the military. That would be the people who would start ordering SMRs first. But suddenly, the data centers has jumped up, and now it's data centers. So I don't have a crystal ball on how big this market will be. Do I think it'll be big? I think for time it will be. Unless we can come up with CPUs and GPUs that run on a new technology that doesn't use power, what I understand is it's almost impossible now to make them more efficient to do the same thing, which just means you make them bigger if you want more. Hopefully there'll be a technology change that will overturn that. So if that's good, I'll go to the next answer, which is the last one from Sanchez Sarencia. What are the most critical materials to be considered in the future of nuclear reactors? Maybe tungsten and the most relevant, a ceramic. Iron is cheap. We would like alloys to be based on iron. However, having said that, for high temperature applications, people are looking at nickel, but nickel activates, and so that's considered to be an issue. You mentioned tungsten, a refractory metal, and yes, very high temperature, very high density. Um, but is that the best? And so ITER, which is the International Test Experimental Reactor for Tokamak Technology, is planning to use some tungsten alloys. I don't think it's an issue for me to say that the fusion company that called me last week, I think it's okay to say they're looking at vanadium because of the low activation and a resistance to swelling inherently in it. In terms of the ceramic materials, and Jason, correct me if I get anything wrong about this, the silicon carbide is very hot right now in terms of it having some good properties for reactors, and continuing to develop our ability to fabricate and join silicon carbide to make it lower cost to build structures out of it. Um, it's looking good. What about other materials for that? One of the things that's a little annoying is silicon can be transmuted to aluminum. So there's some question about long-term high fluence irradiation of silicon materials. So is that a problem or not? Um, One of the other things that is being considered very strongly is high entropy alloys, or what are now called compositionally complex alloys. And the reason for that is if you're going to be slamming neutrons into a material and stirring up the atoms, then you're increasing its entropy. Well, why not start with something that's already in a high entropy state? It's already very disorderly. So that has some potential, but that's a whole new area of materials we don't know a lot about, much about yet. And I don't think Charmayne is on anymore. I don't know if her laptop survived, but glasses. Once again, you're looking at a somewhat disorderly material. Yes, it has local short range order. So how does it respond to irradiation? And creating defects uh, in ionic materials creates ions, charged defects. And so I think there's some potential down the road there, similar with maybe with the glasses. So we're past 3 o'clock. I'm not sure what the pleasure of the group is, but Jason, I'll turn it over to you.
Yeah, and just I guess to quickly follow on there, and maybe some of my own opinions here, but on the ceramic side, you can really, in my personal opinion, look at the roadmap for aerospace and materials they've used there for higher and hotter, and there's similar interests in the nuclear community, right?
Mhm.
You went from iron-based, steels to nickel-based alloys, and then you're moving into ceramics like, SiC or silicon carbide. I do believe, some of the ultra high temperature ceramics have a potential there, the borides, nitrides and carbides. I've been, talking with some fusion reactor companies recently. There's a lot of interest in tungsten diboride or tungsten borides for shielding of fusion reactors, right? Having neutron absorption and high temperature properties there. So I think you can look a lot at aerospace kind of for the roadmap of where maybe ceramic materials may be going and may be beneficial. Um,
Mm.
but to something you said earlier, right? Development cycles for these materials, a lot of these aren't deployed on aerospace, commercially or governmentally yet, and they've been looked at for, 50, 60 years. So there's, a lot more development needs to be done. There's a lot more money that needs to be put into the R&D to really get these materials so they could be, stamped, Q&A for nuclear deployment.
Mm. Well, I'm going to have to move on here in about 5 minutes, Jason. So, or you want to close or?
Yeah, I don't see any other messages. So I just, Joe, thank you again. That was a great talk. And I want to just thank everyone who was here and who came and listened. So with that, we'll close out here. But thank you, everyone.
Goodbye, all.